In this tutorial, we're going to talk about superposition of forces. And for the learning target, you need to be able to solve for the concurrent forces acting on an object using the component method of vector addition. So when you see concurrent forces, it means that there are forces that are acting simultaneously on an object, and your goal is to solve for the resultant force, meaning to say it's that single force value that is equivalent to all those concurrent forces that are acting on that same object. So for the first problem, to release a car stuck in the mud, workmen use 3 horizontal ropes, producing the force vector shown in the figure below. Below or on the right. Find the x and y component of each of the 3 pulls. And then B, use the components to find the magnitude and the direction of the resultant of the 3 pulls. Okay, so this is our problem. And if you look at the required to find, first you have letter A, find the x and y components of each of the 3 pulls. And then for B, you need to use the components in part A to solve for the magnitude and direction of the resultant force of these 3 different pulls acting on the car. So for you to do that using what we call as the component method, the first best thing to do is to set up a table that looks like this, because it will make you easily visualize what you're doing conceptually, and you'll be able to grasp this problem solving skill more effectively. And as you can see in the first column, you just need to list all the forces that are acting as listed or shown in the diagram. Then you need to specify the angle that they make from the positive x-axis, and then just my preference, let's measure these angles counterclockwise from the positive x-axis. Your teacher may teach you otherwise. Maybe they can use y-axis, which would be weird. But yeah, in the steps that I'll be teaching here, our reference point, the reference point that we must be using is the positive x-axis. We're going to measure all angles counterclockwise from that. And take note, when you measure the angles counterclockwise from the positive x-axis, it will take a positive sign as opposed to clockwise. That's why I actually personally prefer this. And then for this third column, you're gonna list all the x components of the 3 forces acting, or whatever number of forces you have. And this last column, f sub y, this will be the column where you list all the y or vertical components of the different force vectors acting. So first, let's do the first column. So f sub 1, we have 790 newtons, and then the angle it makes from the positive x-axis is 124. Miss, how did you know? Because it says here this is 34, and then from the positive x-axis, you have to add 90 degrees because this is 90. So 90 plus 34. So you get 124 or 124. For force vector number 2, it is 960 newtons, and for the angle it makes with respect to the positive x-axis, you have 31 degrees, so it's here. And then for the third force vector, you have 405 newtons. And then what's the angle it makes with respect to the positive x-axis? If you measure counterclockwise, that will be 90 plus 90 plus 54 degrees, and that gives you 234 degrees. So now that we've listed all the forces that are acting, and we have all the magnitudes and directions in place, I'm going to teach you now, or I'm going to explain how to solve or how to determine the x components of all these forces acting on the object. So first, imagine this Cartesian plane. This vector or this vector arrow could represent the actual force vector acting on an object. Let's say it could be this one. And if you have a force vector that looks like this, of course, it has a y component, and it will be pointing upward in this case. And then it also has a horizontal component, and we call it f sub x. Now, this f sub x in this illustration is what we are trying to solve for here, if you represent this stuff trigonometrically. And if you want to solve for this, you have to take note that, well, first you have to imagine you have a right triangle in here, and it has an angle with respect to the positive x-axis. Now, in this case, your force vector here, the actual force acting on the object, could be the hypotenuse because it's the longest side of the right triangle you see. And then this f sub x is actually your adjacent side. Now, since we're looking for that equation that can give you our x component of force of the force, then you basically need to solve for the adjacent side, okay? And because you know your hypotenuse, the best trigonometric function to use is the cosine function, because cosine function based on the SOHCAHTOA is adjacent over hypotenuse side. And then since we're looking for the adjacent side, or f sub x, we're gonna do cross multiplication And if you do that, you're going to have adjacent side equals hypotenuse times cosine theta. Now, we're going to replace these trigonometric terms with physics terms. What we're going to do is rewrite it like this. There's nothing bloody in here. It's just that adjacent side is the f sub x, or x component of force, that we are aiming to solve for. And then the hypotenuse, of course, is the actual force vector, these vectors specifically. So that would be f. And then we just affix cosine theta. It's still the theta that we measure with respect to the positive x-axis. So in short, what it's telling us is that whenever you have a force vector f, if you want to know the x component of that force, you just need to do f sub x equals f cosine theta. But take note, this is only gonna be correct if your angle is measured with respect to the positive x-axis. It's because of the way we derive it. If the theta you're using it is measured with respect to the y, for example, then it's actually gonna go wrong. It would have to be sine theta. But I'm not gonna delve deeper into that. It's just basic trigonometry. So again, this is the formula that we're gonna use. At this point, we're now gonna solve for the x component of force number 1, or force vector 1. So again, if this is the equation, nothing bloody, it's the one we just derived. You notice I just added the subscript 1 in our expressions for theta, for force vector, and for f sub x to represent that this is for force vector 1 specifically, because we have 3 forces here, so we don't get confused. And the next, we plug in the given. So force vector 1 has a magnitude of 790 newtons, and then cosine 124 degrees, because this force vector has an angle 124 degrees with respect to our x-axis. And then you do that in your calculator, you're supposed to get negative 442 newtons. So you write that in your table. So it's pretty simple. Now you do the same for the rest of your forces. To solve for the x component of force number 2, same equation, we just made the subscript 2 instead of 1, of course. Then you plug in the given. So for force vector 2, it's 960 newtons, 31 degrees from the positive x-axis. So there you have it. And then next, if you do that in your calculator, it will give you 823 newtons. So it's here. And then for force vector number 3, we're gonna do the same thing. So it's gonna be, the equation will look like this. Now you plug in the given. So force number 3 is 409. And then the angle for that force is 234 degrees. So this is your expression. You do this in your calculator, you're supposed to get negative 238 newtons. Okay? So now these are the x components of all these forces, meaning to say, these 3 forces, each of them, they have an effective force along x equivalent to this particular value, meaning to say these are the strengths of the forces that they impart along the x-axis. Yeah, they're acting diagonally, all of them, but these are what they specifically contribute to the x-axis of this particular object, the car. Now, how do we solve for the y, or vertical components of these force vectors? So again, let's refer to the same triangle, but this time we'll be deriving an expression for force sub y, or f sub y. So f sub y is represented by this upward vector arrow, okay, obviously. And then that is the opposite side. If this is the theta that we're looking at, it's your opposite side. And the trigonometric function that can help you solve for the opposite side, if you know your hypotenuse, is sine function, because it's opposite over hypotenuse. And we want to isolate the opposite side because it's what we're looking for. We're deriving an expression for f sub y. So we cross-multiply this expression. It becomes opposite side equals hypotenuse times sine theta. Now we rewrite this equation. So we use physics terms instead of trigonometry terms. And this will become f sub y equals f sine theta. Nothing bloody. It's just that opposite side is actually f sub y based on our reference triangle. And then the hypotenuse is still the actual force vector that we are dealing with in this illustration. And then sine theta as is. Now, in short, we can, whenever you have a force vector f, you can determine its y component, or f sub y, by using this expression, as long as, again, the theta that you are looking at or you are using is measured with respect to your positive x-axis, okay? So let's now solve for the y component of all our 3 force vectors. So first, for the y component of f sub 1, that will be f sub 1y equals f sub 1 times sine theta sub 1. Okay, nothing bloody. It's just the general equation we derived, but we added the subscripts 1 to specify that we're dealing with force number 1 and avoid confusion. then plug in. So 790 times sine 124, these are just the given. And you're supposed to get 655 newtons for your F sub y for force 1. Next, you do the same for force number 2. Same equation, subscripts 2. And for force number 2, you have 960 newtons and then 31 degrees for the angle. So there you have it. Use your calculator. You're supposed to get 494 newtons for the y component of force number 2. Next, solving for the y component of force number 3, it will still be the same equation with subscripts 3. And then you plug in the given. So force number 3 is 405 newtons times sine 234. That's just the given. We're just plugging in. And then you do this in your calculator. Then if you can do it mentally, why not? So the y component of force number 3 should be negative 328 newtons. Now take note that the signs make sense. For x components of force, you actually have negative for force vector 1 because it is leftward. Same goes for force number 3. But force number 2, which is projected rightward, has a positive x component. So, and then for y component, force 1 and 2 are positive because force 1 and 2 are both upward. But for force number 3, it has a negative y component because you can see it is directed downward, okay? Now, what do we do next? We're actually done with letter A at this point to find the x and y components of each of the 3 pools. Okay, so these are the x and y components of all those 3 pools. But for letter B, it says here, use these components to find the magnitude and the direction of the resultant force of the 3 pools. So how do we do that? The next step after getting all the components is to add them separately. Meaning to say, we're gonna add all the x components of force. And then what you're supposed to get is 142 newtons. Nothing bloody, it's just negative 442 plus positive 823 plus negative 238 newtons. So this is 143 newtons. What does the number physically mean, miss? Okay. This R sub x, it's not your doctor's prescription. This 143 newtons is the sum of all the x components of the forces that are acting on the car. Meaning to say, overall, guys, these 3 forces have an effective horizontal force of 143 newtons. Meaning to say, yeah, there are 3 separate forces, but if you could have a single force vector representing the 3 of them, then that force vector would have an x component equal to 143 newtons, okay? So that's the physical meaning of that. And then you do the same for F sub y. You add 655 newtons plus 494 newtons plus negative 328 newtons. You're supposed to get 821 newtons. What does it mean? What's R sub y? It simply means that these 3 forces acting on the car, if you were to represent them with a single force, then that single force vector would have a y component of 821 newtons. So this is the overall contribution or effect of all those 3 forces along the y component. They're equivalent to an 821 Newton vertical pull, specifically upward because this is positive. Okay, so that's it. Miss, is that the final answer? Not yet. Those are just the resultant of the x and y components of force. How do we get the actual resultant that's being asked in letter B? So, write them on the side and then you imagine them in a right triangle so we can use trigonometry, okay? So for R sub x, that resultant force along x could be a rightward force vector. So we call it R sub x. So this force vector, which is rightward, could represent this 143 Newton force. And then this R sub y could be represented by an upward vector arrow. Now take note that the length of these force vectors are not scaled based on these values. I'm just using this to represent how they could look like physically. So this is a generic illustration. If you were to scale them, then of course R sub y should be longer. Yeah, but this should suffice. Let me clean that first. So that's it. And then now that's R sub y again. So for you to know the resultant of this R sub x and R sub y, of course, in vector addition, you remember, in polygon method, you just do put that resultant or draw the resultant vector force from the tail of the first vector to the head of the second vector. And this is your resultant force, okay? So again, if you draw this arrow from this tail of the first vector towards the head of the second vector, that will be representing, or that will represent your resultant force that we are solving for in letter B, okay? So that R is what we're gonna solve for. And based on the illustration, as you can see, you have a right triangle in here. To know the value of R, all you need to do is to use not Sokotoa. It's the Pythagorean theorem, which is C squared equals A squared plus B squared. Because you have a right triangle, and if you want to know your hypotenuse, definitely, you can use your Pythagorean theorem. And then next, we get the square root of both sides of the equation to cancel this exponent 2 because we want C to just be C. So it will become C equals square root of A squared plus B squared. And then we rewrite it using our physics terms. Nothing bloody, it's still the same equation. But instead of writing C, we write R because C is the hypotenuse of our right triangle in Pythagorean theorem. And that is also represented by our resultant force that we're looking for in part B. And then take note that A and B are just the two other legs of your right triangle. It doesn't matter which is which, but we could write R sub x and R sub y for A and B respectively by choice. And then we plug in the given. So R sub x is 143 newtons and then R sub y is 821 newtons. So there you have it. Do not forget the exponents because obviously your answer will be wrong if you forget those little details. If you use your calculator, you're supposed to get 833 newtons for the resultant force of all these three pulls. Now take note, what we have so far is only the magnitude of the resultant force. Since force is a vector quantity, you also need to give the direction, okay? But how do we solve for direction? If we use the Pythagorean theorem to solve for the magnitude of the resultant force, what we're gonna do to solve for the direction is, well, first take note that you have here your theta. This is our angle, a reference angle. And then if that is your reference angle, R sub y is the opposite side, obviously, and R sub x is your adjacent side. So take note that knowing the opposite and the adjacent side, we can use the tangent function to solve for the direction of the resultant force, which is just this angle, basically, okay? So opposite over adjacent, and then, because we want to get rid of the tangent expression for us to know theta, what you need to do is to take the arc tangent of both sides of the expression, because if you do that, you can cancel the tangent expression in here and you will be left with theta. And then of course you distribute the same thing on the right side. You're gonna have theta equals arc tangent times R sub y over R sub x. Take note that some references would use tangent raised to -1. That's also correct. Next, let's plug in the given. So R sub y is 821 newtons, R sub x is 143 newtons, and what you're supposed to get there is, for the theta, is 80.1 degrees above the positive x-axis. So that is the final answer for the direction. Wait, miss, okay. First question, how did you know it's above the positive x-axis? Well, first, based on the illustration, it should be above the positive x-axis because you have a positive r sub x and positive r sub y. Yeah, but as a general guideline for that, if you have a positive r sub x, then it will be in the positive x-axis. That's the first point. Second point, you might be asking, yes, miss, okay, positive x means positive x-axis, but how do you know the above or below? Well, simply because if r sub y is positive, it will be above the positive x-axis. So that's it, okay? So again, the guide for that is here. So if r sub x and r sub y are both positive, then the direction is above the positive x-axis, so on and so forth. I think as a rule of thumb, your main basis here should be the idea that whenever r sub x is positive, obviously, your resultant force is in the positive x-axis. And to know whether it is above or below the negative x-axis, then your reference is y. If y is positive, then it's above the negative x-axis. If it's negative, then it's below the negative x-axis or whatever x-axis there is. Okay, so that's it. Also another concern, you might be wondering, miss, how do you do this entire thing? In your calculator, yes, miss, I have a calculator, but how do you do arctan 821,143 stuff? Okay, this is what you do in your calculator. So this is what you're solving for, right? What you need to press in your calculator is 821, division sign, 143, press equal sign, and then press shift for other calculators like sharp, its second function, and then press tangent or tan, and then press the equal sign. You're supposed to get 80.1 degrees for that, okay? And then just add the above positive x-axis, blah, blah, blah. So this is the final answer for letter B. Okay, what is the direction and magnitude of the resultant of the three pulls that is A 33 newtons, 80.1 degrees above the positive x axis? So this is our final answer for letter B. And then again for letter A, those are all in the table. Okay, does it make sense? Yes, based on the relative magnitude of these forces as well as their direction, it's reasonable that the resultant force is above the positive x-axis, so somewhere in here. So again, the physical meaning of this answer is that that is that single force vector that could represent the overall effect or impact of all these three forces acting simultaneously on the same object, which is the car. Now, for our next problem, three professional wrestlers are fighting over a champion's belt. Each of them exerts forces on the belt as shown in the figure. So that's the top view. The forces have magnitudes 230, 52, and 127 Newton. Determine the x and y components of the net force on the belt and the magnitude and direction of the net force on the belt. So take note that the term net force and resultant force or resultant are just referring to the same thing, so do not be confused. So this is just a very similar problem. It's just that you have a different setup given. So again, for you to know the forces or the x and y components of the net force on the belt, then you need to set up this table, list down the forces. So that's 230 Newton. And then for the angle, it's 137 from the x-axis. Miss, how do you get 137? Again, this is force vector 1. So this is 180, this entire thing, right? 180 minus 43 will give you 137. So this is 137, okay? So that's our angle for force 1. For force 2, it's 52. It's directly... for force number 2, it's 52 newtons rightward. And then for the angle is 0 because force 2, let me just clean this board so you can see this properly. Yeah, so you can see force number 2 is directly along the positive x-axis. So the angle you're going to report is 0 degrees because it's directly overlapping with the positive x-axis. Force number 3, it's 127 newtons. Okay. So how far is this from your positive x-axis? So this is 90 plus 90 plus 90. Then you have 270 degrees for the angle of your force vector 3. For the x component, again, the equation is just f cosine theta. To know the x component of any force is just f cosine theta, as long as the theta you're using is measured with respect to the positive x-axis. So it's here. And then plug in, so that's gonna be 230 times cosine 137 for force 1. Just plug and chug. Use your calculator, you're supposed to get negative 168 newtons. Now, do the same for force vector number 2. So, it's still gonna be the same equation with subscripts 2 instead. And then you plug in, it's 52 newtons at 0 degrees. So, your x component would be 52 newtons. Now, take note, actually, for force vector number 2, it's actually quite obvious. I mean, force vector 2 is directly pointing rightward. So obviously, the x component of that force is the force vector in itself, 52 newtons, because it's pointing to the right. That's the x component itself. And then next, but yeah, if you want to justify mathematically, there you go. X component of force vector number 3, again, same thing, f cosine theta. Then you plug in, it's just 127 newtons times cosine 270. Use your calculator, you're supposed to get 0 newtons. And actually, just like with the case here earlier, you can actually see that you have a downward force, right? So if you have a downward force, obviously, the x component is 0. It's not imparting or contributing anything to the x component. So obviously, if you have a downward or upward force, the x component would be 0. But again, if you want a mathematical justification, there you go. Next, let's solve for the y components of these three force vectors. Again, for the y component, just use f sine theta. Okay? As long as the theta is measured from the positive x-axis. Then you plug in, it's just 230 times sine 137. A very similar solution with x component, but this time we're using sine. You're supposed to get 157 newtons. And then for the second force vector, same equation. To know the y component of force vector 2, then you do f2 sine theta. Plug in, so it's 52 times sine 0. Okay, so you're gonna get 0 newtons, okay? And that's obvious because force vector 2 is horizontal, so the y component is 0, obviously. And then for the third force vector, it's f sub 3, so that's gonna be 127 times sine 270, and you're supposed to get negative 127. The answer makes sense because if you have a downward force, obviously, that in itself is also the y component of that force. But take note, the negative sign will come out because the y component of this force vector is pointing down, okay? What you need to do next is to solve for the net force on the belt by determining the magnitude and direction of that net force. For you to do that, first thing you need to do, add all the x components of the forces acting on the belt. So that's gonna be negative 168 plus 52 plus 0. It will give you negative 160 newtons. Next, add all the y components of all the force vectors you're dealing with. So that would be 157 plus 0 plus negative 127. It will give you 30 newtons, okay? By the way, at this point, we have answered letter A. It's asking us to solve for the x and y components of the net force on the belt. By the way, the question here, to be clear, is the x and y components of the net force. So take note that r sub x and r sub y are the x and y components of the net force that we will solve for in the next slide. And again, to know the resultant force, let's represent them with a vector arrow. So this r sub x is negative 116. So it will be pointing leftward like this. And then this r sub y is 30 newtons positive, so it's upward, okay? And then what would be the resultant, or how will it look like? The resultant force would be, again, from tail to head of the first and second vectors. You draw that vector arrow. That is your resultant force, okay? And to know the magnitude of that resultant force based on the illustration, it's just gonna be, you're just gonna use Pythagorean theorem. So it's c squared equals a squared plus b squared, okay? And then you replace those trigonometric expressions with physics expressions. So c is the longest side, which is the r, or resultant vector we're looking for. And then a and b are the two other legs, so r sub y and r sub x. Next, we plug in the given. So r sub x is negative 116, r sub y is 30 newtons. And then if you solve for r using your calculator, you're supposed to get 120 newtons for the magnitude of the resultant force. Now, for the direction, you're supposed to get, or you're supposed to use tangent function because, again, if this is your theta, the one touching the x-axis, r sub y is your opposite side, and r sub x is your adjacent side. So you can use tangent function to take into account those known values, r sub x and r sub y. And then, again, we take the arctangent of both sides of the equation because that will allow us to cancel tangent and then isolate theta. And then the equation will look like theta equals arctangent times r sub y over r sub x. We plug in the given, so r sub y is 30 newtons and then r sub x is negative 116 newtons. In your calculator, you're supposed to get 14 point something, but please round it up to 15 degrees. And then you might be saying, Miss, I'm getting negative. Okay, well, the negative sign might be confusing if you use that in your theta. So what I would suggest you to do is just leave the theta as positive and then state the above the positive or negative x-axis expression. Because if the theta is negative, it may not make sense immediately. Like you'll ask yourself, why is the theta negative? Does it mean it's below the is it because is it negative because it's below the Cartesian plane, or is it because on the left side of the Cartesian plane? There are some ambiguities like that. So what you need to do with the theta is, even if it comes out as negative, make it positive, and then to be specific with where it is measured, you say something like above or below the positive or negative x-axis. And again, why is it above the negative x-axis mean? So based on the illustration, if you look at the illustration, that's one, it's above the negative x-axis. But apart from that, if you're just looking at your equation, you can see that r sub y is positive, so it's above your Cartesian plane. And then the r sub x is negative, so it's in the negative x-axis. So it's that simple. So the final answer for the theta is 15 degrees above the negative x-axis, okay? And again, if you were to report your final answer for letter B, your resultant is 120 newtons, 15 degrees above the negative x-axis. So, because it is 15 degrees above the negative x-axis, it simply means that the belt will accelerate towards this way. And obviously, it's actually wrestler number 1 who is winning this this champion's belt. I don't know, maybe it's John Cena or Batista. We don't know, but must be someone really strong. Yeah, so that's the idea of like getting the resultant force, because if you have these three forces acting simultaneously, and the resultant came out to be like this and it's above the negative x-axis, then it simply means that the acceleration of the belt will be that way, okay? Because that's it. The idea of net force tells us that wherever the net force is pointing, that's also the direction of the acceleration, right? So that's it. In the case of the car earlier, the resultant force was in here. So that means that the car will accelerate this way. I think, yeah, I believe it's in quadrant 1, right? So that's the idea of net force. Anyway, that's all for this video. This is a summary of the problem solving steps. You may take a screenshot or copy this in your notebook. That's all for this tutorial. Thank you so much and have a great day.